Very first things that we are going to go over right now in physics are the basics of motion. So we have to talk about position and velocity. Position is simply what you're used to. It's where you're at. Velocity seems to be how fast you're going, and it is with a little tweak. But before we actually get into that, we need to get common language. So let's knock out some definitions here on the first slide. Distance is how far away an object travels. Its base unit is meters, and it seems like it's the same thing as the term displacement, one that we are going to use all the time, but it's slightly different. They both have base units of meters, but displacement is the direct line distance between the start and the finish. So imagine starting right here and then driving your car along the road, and maybe it requires that you go all around like this to get to your finish. That's the distance you travel. Displacement, listen to the word, displacement, the distance between your placements. That's going to be your direct line distance from start to finish, and it has a definite direction, whichever direction you actually were going. So to indicate that, we're going to put an arrow tip over here. In fact, all vectors, which we're coming to here in a second, all vectors we indicate with arrows there, trying to show its direction. In fact, displacement is a vector, meaning that it has a measurement, how far you went, and a definite direction, a single definite direction. Whenever we say the word magnitude, we mean number value. A scalar is just a measurement. It doesn't have a direction, or its direction is always changing, and so we can't say that. Distance is a scalar. Now, speed is something we talk about all the time. It is how fast you are going. Sorry for the double fast there. Let's get rid of one of those. Base units of meters per second. Now, velocity is very similar to speed. It is how fast you are going, but in a direction. In fact, velocity could be said to be speed plus a direction here. But there's a more technical definition for velocity. It's the rate of change of displacement according to time. Base unit meters per second also. We'll talk more about that definition on the next slide. Now, constant velocity isn't when an object is moving at the same speed and in the exact same direction. Instantaneous velocity is the velocity at one specific moment in time. Average velocity is your average speed and your average direction that the object ends up moving. Now, there are two key things you need to get out of this lesson. First key thing that you need to get out of it is what is the equation for velocity, and then how do we use that equation to solve problems? V equals something. The second main thing you need to get out of this lesson is on a position time graph, how can I find the velocity? Now, to figure this out, let's first dissect the definition of velocity, and then let's do a little thought experiment to maybe figure all of this out. Velocity is the rate of change of displacement according to time. If you remember from your math classes, rate of change means slope of a graph. If you didn't get that in a math class, that's okay. Write that down somewhere. We're going to be using that all the time this year. Rate of change means slope of a graph of, this would be our y-axis, displacement, and this would be our x-axis, time. And so whenever we were actually going to talk a graph here, there's a reason why we do a position time graph, because change in position is displacement, aka on the y-axis, and time on the x-axis. Now, I want to set up a car down here. Let's let this car be going at some constant velocity that we want to figure out. Constant velocity means same speed, same direction. So let's put the car going 0.5 seconds, it makes it a meter. Another 0.5 seconds, it goes another meter, so forth and so on. Now, let's actually graph out the car's motion on a position time graph. So it looks like every 0.5 seconds, I need to make a mark, 1 meter mark, another 0.5, 2 meter mark. Let me do that really fast for us. Well, now that I have all my dots down there, let's hit it with the best fit line or curve. It looks like it's linear, something like that. Sorry for the wavy hand there, also not on graph paper, so things don't turn out completely right. It looks like for a constant velocity, the graph for constant velocity on a position time graph should be linear, should be going up something like that in a straight line. Now, let's go back to our definition here. Velocity is the rate of change, aka the slope of a displacement time graph or a position time graph here. Let's figure out the slope of this graph then, since that seems to be the definition. Slope equals Rise over run is how most kids come to me saying the equation for slope. And I want to write that down, and then I'm going to erase it right now because I want to use a slightly different but yet meaning the exact same thing equation. Slope equals change in y, change in the y-axis. That triangle is the Greek letter delta, meaning change in, aka the rise. Change in the y-axis divided by the change in the x-axis, aka the run, how far out you go there. Well, what variables do I have on the y and then the x-axis? This would tell me that the slope here, if I just write in the variables I have, is going to equal the change in position. Change in position, well, that's the term displacement here, divided by what's on the x-axis, time. Change in time we can just call time because, well, time is always moving. That actually gives us our equation. The velocity is the rate of change, aka the slope of the displacement time graph. Slope is displacement divided by time, so velocity has to equal displacement divided by time. Maybe we should finish out that term, which gives us our equation here. V equals S over T. So that gives us our equation, velocity equals displacement divided by time. We're using the letter S, the variable S, to stand for displacement. So be careful with that. S is displacement. It's going to be that way from here on out, so don't get confused. All right, that was one of the things that we had to discover was what was the equation. And en route to discovering the equation, we got the other thing. On a position time graph, the slope gives us the velocity. So the two big things that you need from this lesson really is this idea and statement, and then we got to be able to apply it, and this equation here, and then we need to be able to apply it. Thus on to the next slide. Now let's talk good problem solving skills. Whenever you're doing word problems, first thing that I want you to do is to underline the things that you know and what you are looking for. Key terms that you need to listen for. How long means solve for time. How far means solve for displacement. How fast means solve for velocity. Other good problem-solving techniques. Make a variable bank. You'll see that coming up in a moment. Rewrite the equation, then substitute all of the numbers into the equation on the next line down and work the algebra line by line. You're going to hear me say that a lot this year. Students come and they get this first lesson and they think they can just do it in their head, and for the most part they can. And then by lesson 3, the music has changed, so to speak. Things have gotten a lot harder, and if they don't pick up these basic problem-solving skills, they struggle a lot. If they'll do the basic problem-solving skills, lesson 3 is easy. All right, I have a car. It's going to drive 54 meters. That's the displacement, S, in 12 seconds. That's the time. Calculate the car's average velocity, V equals question mark. So I went ahead and made my variable bank off to the side, and now I'm going to rewrite the equation that I'm going to use. This car is going, we're calculating the car's average velocity, so we'll use the average velocity equation. It's the same as the constant velocity equation. Maybe we'll put a bar over the top to indicate that we're looking for the average. Now, truthfully, the physics is done. I'm just going to simply start doing my math problem now. I'm looking for the velocity. The velocity is the unknown, so I'll keep the V as the unknown and substitute in what I do know. 54 for the displacement, 12 for the time, 12 seconds. Work the algebra. It seems here that all of the algebra is already done. The V is already by itself, so I just need a calculator. So the average velocity of this car turned out to be 54 meters per second. Base unit meters per second plus, check it out, I did a meters divided by a second, so the unit for velocity must be meters per second. Let's go ahead and do another example problem using the equation. Usain Bolt, he's the 100-meter world record runner, can run 100, I need a unit there, sorry about that, meters with an average velocity of 10.4 meters per second. This is my displacement, this is my velocity. How long, key term for time, how long will it take Bolt to run the 100-meter race there? How long? Sometimes kids get confused with that key term. Think about being in a car on a road trip. Whenever you ask how much longer, you're asking how much more time do I have to sit here. So now I've done my variable bank. I'll rewrite my equation, v equals s over t, and this is an average velocity. We know that a runner doesn't run at the exact same speed the entire time. I can substitute in and then solve. So I'll put 10.4 in where the velocity is, 100 meters in for the displacement, and the time is unknown. Now this actually does require a little bit of algebra. The first thing I've got to do is get the variable, the t, out of the denominator. So I'll multiply the t to the other side, so it crosses out over there. So now I end up with 10.4t equals 100. The next step is to get the t by itself, divide both sides by 10.4. So it crosses out over there. So t is going to be whatever 100 divided by 10.4 is. That turns out to be 9.6 seconds. Notice how I worked this problem. I rewrote the equation, I substituted in what I knew, and then I worked the algebra line by line by line by line to make sure I wasn't making a mistake. All right, let's jump up here to number 2, and we're using the same car from number 1. Not that that really matters. The car then speeds up as shown in the graph, and I have a position time graph. Determine the average velocity of the car. So I'm looking for v equals question mark, and in a position time graph, the slope of the graph is the velocity. So what I need to solve for here is the slope. Slope equals change in y divided by change in x, aka the velocity here equals the change in y divided by the change in x. It looks like, if we are going to write this out here, change in y is going to be, maybe you are familiar with this version of the slope equation, y2 minus y1 over x2 minus x1 here. That's going to be slope equals 30 minus 0 divided by 6 minus 0. I went ahead and I added in quickly labels. Remember, this is the second point because we're going this way on the graph. So here's x2, y2. This would be x1, y1. Since we started from 0, 0, that's why the y1 and x1 points were 0. So this can just be plugged into the calculator now. 30 minus 0 divided by 6 minus 0, that's 30 divided by 6. 5 meters per second. Check out the units on the graph. Meters per second. Now in problem number 4, I have a plane that didn't seem to start from the origin. Started from check out the units, kilometers over here. 1 kilometer past the origin, whatever the starting spot could have been. And then it looks like it doesn't fly at a constant velocity. Notice how the slope is always changing. In fact, at one point, it actually turns around and comes back down maybe to wherever it's going to land. It goes too far, it has to turn around and double back. And I'm asked for the average velocity again, and you might think to yourself, how on earth do we do that? V equals question mark if it's not a straight line. What we're looking for, the average velocity, means we're looking for the average slope of the graph. Now that might feel a little crazy, but we can actually easily get the average slope of the graph by finding the slope of a line that connects the first point and the end point, which I mostly drew there. Somewhat difficult to draw freehand without a ruler. So find the slope of the line that connects the first point and the last point. Well, that's not a big deal. Slope equals y2 minus y1, x2 minus x1, and I've got my points, right? Here's x2, here's y2, and here's my x1 and my y1 down there. Not a problem. So after substituting that in, I end up finding that the velocity is 0.5 kilometers per minute. And you might say to yourself, hold on, Mr. Birch, you've said that the base unit for velocity was meters per second. Why are we dealing with kilometers per minute? Well, that's because that's what the units were given to me on the graph. We'll talk about converting units in an upcoming video here. So velocity, the average velocity would be 0.5 kilometers per minute. Yes, the velocity was changing. Here the velocity was low. Here the velocity is really high. Look how steep that slope is. Right here the velocity is 0. The slope of the line is 0. Here the velocity is negative, but the average velocity is the slope of the line connecting the 2 points. So I'm able to calculate the average velocity that way. All right, very good. Your first video. I hope you got everything down. Make sure that you write down any questions that you have, because we'll start out class after doing a little starter or a do now, if you will. We'll dive right into what questions you might have about this video.